This is a joint work with Yu Pang, who is currently at the School of Business at Macau University of Science and Technology. And this, as you see, is about regulation and pollution abatement in the event that economies of scale matter. So this paper is going to be a theory paper because I am a theory person, so I am an IO person. So this paper is going to address the regulatory problem of overcoming negative externalities caused by environmental pollution in contexts in which there are also positive externalities associated with economies of scale, cost savings associated with scaling operations in settings of monopolistic competition. So we are going to address this regulation by means of, well, pollution standards and also taxes. Well, I think one prominent example is the fashion industry, which is, as you probably know, one of the main industries responsible for global emissions, around 10%, just after fuel and agriculture, and also responsible for a lot of waste, especially if we think of the fast fashion industry. At the same time, this industry is not only highly pollutant, but also, I think, enjoys lots of economies of scale in the many phases. So not only the production phase, but also in the distribution, in the retailing stores, and also, as you can imagine, a lot of expenses associated with publicity, big publicity costs, advertising, all this story now with influencers, etc. That we think they matter a lot. Our question is how we can correct for environmental externalities in industries characterized by economies of scale. So basically, big fixed cost associated with production. We are going to do it by means of two instruments: an emission standard. We are going to refer to it as a required emission intensity, or an emission tax or a required fee per unit of pollution. The idea behind this question is because we realized that there is not much literature about that. In fact, there are a few theoretical papers by our keynote this morning, a long time ago, with some co-authors, Still Recuate and Quas. It was, in fact, very difficult to find some of these papers. Some of them are hidden in book chapters. So this was like a long time ago, and then suddenly in a few years we have like several empirical papers looking at these issues again, and then we thought it was probably a good idea to write a model based on all this previous literature. There is also a very recent paper by two colleagues of us in Valencia, Casino and Granero, who are working exactly on the same topic, but with another type of model, with a spokes model, which is a variation of the hoteling model. Well, basically what we do is to use the standard analytical framework by Dixon and Stiglitz, and also Krugman, in which there are differentiated firms, but in their setting, each firm's choice exerts little impact on the rivals, especially because they use this model, as you probably know, for macro issues, international economics issues, etc. And in fact, there is no pollution in this context. So what we do in our model is to adopt that model, but using a more micro perspective, in the sense that we are going to be especially looking at the strategic interaction between the firms that are involved in this industry. We are going to have firms that generate pollution as a byproduct, and also we will have that firms can abate some of this pollution. This is going to be the roadmap for the rest of the talk. First, I'm going to introduce the model. Then I will briefly talk about the laissez-faire solution, which is, I think, key in order to understand what happens with the different incentives created by taxes or pollution standards. And then we will talk specifically about these two measures, and then I will give you some takeaways. So that's the model. In our model, we have first consumers, or we have a population of identical consumers, and with preferences for end consumption goods. And these consumers also suffer from environmental pollution. This coefficient theta is going to be this degree of differentiation, these preferences for differentiated goods. And also this delta parameter is going to measure how in which way they suffer from pollution. And then we have these consumers that they have, they inelastically supply 1 unit of labor, whose wage is normalized to 1, and then they spend their income in the purchase of these end goods. Regarding firms, we are going to have n firms, each one of them producing a different variety of the good, and then we consider the typical production function used by Copeland and Taylor, that is Jacob-Douglas in emissions and also in labor. And then what is important here is to see that we are going to have this parameter alpha here that is going to be key for analysis, which measures the fixed cost, right? The scale, the degree of the economies of a scale. That is that we need this to spend this alpha in labor units before we start operating. In fact, here you have everything. So you have all the notations. You have individual output. We have emissions, EI, and then labor. This is the fixed cost, and this is also a proxy for the marginal cost. And this gamma parameter reflects the pollution intensity or how dirty the technology is. Then we represent profits as usual with wages normalized to 1. So we have revenues minus labor costs minus any cost associated with the regulation. What is important here is that the number of firms is going to be determined endogenously. In the aggregate or in the equilibrium, we have full employment and also market clearing for each variety of the goods. And also total emissions are defined as the sum of individual emissions. And finally, we have the zero profit condition that, let's say, closes the system. What about the laissez-faire? So in this one, as you know, we define it as a situation in which there is no environmental regulations, and firms do not have, therefore, incentives to abate pollution, and hence pollution is equal to emissions. So we assume that the emission intensity is 1, which is the worst possible emission intensity. And then what we do is that we let firms to choose prices to maximize profits. And then we establish like 2 different behavioral assumptions. One is the strategic assumption in which we allow firms to set prices taking into account that the rivals are going to react to their own prices, which is the micro perspective that I was telling before that we are going to be using. While in the other case, which is we call it non-strategic, is the standard one in which these effects of rivals' prices on own prices are not taken into account. So this would be the traditional approach, and this is the approach that we follow in our paper, and we are going to see that this is going to be key for the results. So these are the steps, the typical steps that we follow in any resolution of any model of this kind. So first we derive individual demands for given number of firms and for given prices. Then we obtain firms' optimal prices for a given number of firms. And finally, in the last step, we impose symmetry, market clearing, and zero profit conditions to determine the endogenous number of firms in this situation. Again, in the second step is key, the behavioral assumption. So there are going to be differences between the two. So the nice thing is that we find explicit expressions for all the main variables, even that the model is not that simple. And then what we can see in the first place is that regarding the number of firms, prices, quantities, individual quantities equal to pollution, and also overall pollution, we can rank perfectly, and for any set of parameters, which model is doing better in terms of each one of the variables. So the first thing that we can see is that, for example, regarding the number of firms, we see that under the strategic assumption, we have more firms. We also have more larger prices. We have lower individual quantities and therefore lower emissions, and also lower aggregate emissions. And obviously, we have done a full comparative studies with respect to all parameters, but for the purpose of this presentation, I will just focus on the first row that determines what is the effect of this alpha parameter, the parameter that determines this scale effect of fixed cost. And we see that it is It has a negative effect on the number of firms as expected. It has a positive or zero effect on the prices depending on the behavioral assumption. It has a non-monotone effect regarding production and therefore emissions, which is consistent with recent empirical literature on this topic. And it also has a negative effect on overall emissions. So I mean, we can see from here that even in the context of the laissez-faire solution, having a large scale seems to somehow benefit a bit the environment in terms of overall pollution. Now, in the second part of the paper, what we do is to solve for the optimum. So this is basically the problem that we solve. So we maximize the utility of the representative consumer subject to the production technology that we are using and subject to the market clearing conditions with respect to all varieties and also of labor, and plus this symmetry condition, and then we find also likely split expressions for, again, all the parameters, which again help us a lot to find clear comparisons with respect to the laissez-faire and also clear comparative static analysis. What we found is that regarding this importance of the scale parameter, the fixed cost, we have that as long as alpha increases, this reduces the number of firms that are going to be in the industry, in the equilibrium. It increases individual emissions, but decreases, as you can see, emissions intensity, and also decreases overall emissions. What we have here is a comparison, and for the purpose of this presentation, I want you to focus just in the first row. What we have is a comparison of the social optimum with the two possible laissez-faire situations we could have, depending on the behavioral assumption I have explained before. And we can see that, so the dot is the optimal. For example, this is for production, individual production. This is for individual emissions, all these are for overall emissions. We can see that the dot is the optimal emissions. The dark, this black one is for the strategic case, laissez-faire strategic case. This one is for the non-strategic case. And we can always see that when we make changes with regards to any parameter, we have that there's always the same rank, right? So regarding individual emissions, we always have that the social optimum induces lower emissions than any of the laissez-faire cases. And the strategic case, as you see, is always in between, right? Always in between the optimal and the non-strategic case. This is always the case for individual emissions and for overall emissions, right? We can also see that as the parameter, as the alpha parameter is large, we see that there is a wider gap, right? Like a divergence. So the need to regulate becomes more and more important when this parameter alpha is large enough. We can also see it here with individual emissions. And what is interesting, so here we have the graphs for all the, you see, for all the variables, and we also see this same ranking between the three. And what is, I think, interesting is that regarding production, and also regarding the number of firms, I do not have it here, but regarding also the number of firms, we have crossing points, right? We have crossing points between optimal individual production, let's say, and optimal production in the laissez-faire when we have the strategic case, right? So the non-strategic case would always go above, right? So more production in the non-strategic case, and when we consider the strategic case, it could be the case that production is either above or below the optimal output. And the same for the number of firms. Okay, we could also have situations of excessive or insufficient number of firms, depending on the parameters. This doesn't happen with individual pollution and with overall pollution. Well, in the final part, so I don't know how much time do I have. 10
minutes.
Okay. In the last part, we have done an exercise. We have implemented an emission tag standard and also an emission tax. the emission standard is simple in the sense that we are going to require firms to pollute according to this intensity lambda. So the smaller lambda, the more intense is going to be the policy, and therefore the lambda equal 1 case refers to the laissez-faire, right? So the lower the lambda, the more stringent the policy is. And regarding the emission tax, what we do is to implement these emission taxes with a transfer payment to the consumers in order to close the system. And therefore, in this second case, what we are going to do is that we are going to assume that each firm is going to pay a linear tax depending on individual emissions. And then each consumer is going to receive a lump sum transfer of total collective taxes in this way, and therefore each individual budget constraint now is going to be this. So we can assume this as to partially compensate for the environmental damages that consumers are suffering. This is the steps in the resolution now, so very similar to the laissez-faire, but now taking into account that we have this policy in place. So the first thing we do is to find the equilibrium for a given instrument, and then in the second place, we find the optimal value for the respective instrument for given parameters. And yes, for the purpose of this presentation, I'm going to focus on the strategic case to try to convince you that in this case we could have this again, these crossing points that are going to induce different incentives regarding the two instruments. So if, for example, we look in the first place at the emission standard, which is a required level of this ratio E over Q between 0 and 1, we see that a decrease in this parameter, so a more stringent policy, a more stringent standard, is going to increase, is going to result in an increase in prices, which is something very intuitive. Also, it's not going to alter n, the number of firms, so it's going to be no entry, no exit of firms with this instrument, and also a decrease in individual production, together with also a decrease in individual emissions and overall emissions. However, if we look at the emission tax, what we have in this context is that if we wanted to increase the tax, so a more stringent policy, what we have in this case is again an increase in prices as in the other case. We also have, as you see, a decrease, going to the last sentence, a decrease in individual emissions and overall emissions, which is also something that we want if we impose a tax. But then regarding the number of firms and the quantity, the output, they could decrease or increase. So we think this is interesting, and this is the main difference between the two cases. So basically, what we can explain by means of this model is that an entry an emission tax does not necessarily mean an entry impediment. So we could have the other way around. Okay, so finally, what we have in this last slide is the response of, well, the comparison of the optimal instrument being either an emission tax or an emission standard with respect to many, the different dimensions of this problem, and also compared to the optimal output, optimal solution. As you can imagine, we have two externalities. So here we have a total welfare. We have two externalities. So these two instruments will only be able to get the second best solution, right? We would need another instrument to get the first best. So since this is second best, we have that, for example, in this particular simulation, we have that taxes are going to perform a bit worse than environmental standards in terms of of social welfare, as I said. But this is just these numbers. We could have also the other ranking, which is also interesting, is that the optimal tax performs, let's say, even a bit better than the social optimum in terms of total pollution, right? So this optimal tax is going to create some let's say, under pollution with respect to the social optimum. All this I haven't said, but all this depends on this alpha parameter, right? However, you see the pollution standard is performing a bit worse regarding total pollution. For example, we have here the output per firm. And in this case, we have that the optimal tax in this particular context is inducing lower production, but the social standard could be inducing either higher or lower production than the social optimum. So you see we have this crossing point here. Regarding the number of firms, we have that the optimal tax might be inducing entry as compared to the social optimum. And what else do we have? Pollution intensity. Here you see the three are decreasing with respect to the fixed cost. That's fine. And also the social optimum is the one that is prescribing a larger, more stringent intensity. Here we have the emissions per firm. Okay, so this is basically the story I wanted to tell. So regarding the contribution, what we have done is to develop a model that addresses environmental regulation with scale economies and monopolistic competition. Regarding the results, I would like to stress 4 of them. First, that the behavioral assumption matters a lot. It's key, and in fact, this strategic case is the one that helped us to obtain this result about the crossing points for both for the number of firms and also for production, which we think is quite interesting and according to some recent empirical findings. There is no obvious comparison between the optimal solution and the strategic laissez-faire regarding individual production and the number of firms. There are very different incentives induced by the emission standard or the tax regarding individual production and the number of firms. And finally, the tax seems to be preferred over emission standards regarding overall pollution and also firm entry, right? So regarding the competition parameters, let's say, or the competition variables, but not preferred in terms of social welfare, at least for the simulation we have carried out in this study. So this is all. Thank you very much.